Hello and welcome to the lecture on chapter 25. Here we're going to talk about electromagnetic induction. All right, we'll find out what that term means. This is also the last chapter that covers electricity and magnetism formally, and then we'll move on to light, which of course is created by electricity and magnetism, but more on that later. Okay. All right, so we're going to define electromagnetic induction, talk about something called Faraday's law, which is also relates to something called Lenz's law. We'll talk about generators and alternating current, so kind of how an AC current is made and why it's made in a generator. A little bit about power production, self-induction, which is also sometimes called back EMF. All right. Power transmission, sort of step down, step up transformers, and then also the concept of field induction, which will be our final topic in our segue to light. Okay, so what is electromagnetic induction? So let's think about what we've seen so far. We have seen that a current creates a magnetic field. So current creates magnetic field, okay? That was in the last chapter, last lecture. We also saw that a magnetic field exerts a force on a current. A magnetic field exerts, on any moving charge, but we'll think of it as a current, exerts force on current. And again, it's not on the current itself, it's on the charges, right? But it manifests itself sometimes as a force that would move a wire. Think about the force between wires. Okay, so these are the ideas so far. And historically, this is what was known for first. But then, okay, so if we have it that a current creates a magnetic field and a magnetic field exerts a force on a current, could a magnetic field create a current? Because we haven't seen that. It seems to be sort of things are going in one direction almost, but can the magnetic fields do something besides just exerting a force? Can they actually create a current? All right, well, let's think about it. So electromagnetic induction, discovered by Faraday and Henry, shows that a voltage can be created by a changing magnetic field. All right, so there we have it. You can create a current and an associated voltage, because once you have a current, then you're going to be able to get a voltage gap, right? You're going to be able to basically, it's because if you have a current, then you're making the charge flow in a certain direction, thus creating a potential energy differential, and then like maybe you're pushing the current uphill, so to speak, right? And so you're giving it potential energy per charge, which is voltage. Okay, so that's why the two ideas go hand in hand. We can say, okay, well, if you're inducing a voltage, then you're also inducing a current. So we finally have the last piece of the puzzle, that a current can be created, but not just by any magnetic field, but by a changing magnetic field. And that is so interesting, right? Because we didn't need a changing current to create a magnetic field. So current can be created by a changing magnetic field. A steady current creates a steady magnetic field. But to get any current at all from a magnetic field, it has to be a varying magnetic field, represented here by the motion of the hand. So you'd have to be pulling the battery in and out, kind of oscillating it, thus changing the actual strength of the magnetic field experienced by the wire in order to create a current. All right, if you held the magnet in there, the magnet would have a constant magnetic field, but that steady magnetic field would not induce a current. All right, it would just, sure, there would be a force on, exerted on the charges if they were in motion, right? But if the charges are in motion, they don't experience a force. So in fact, let me go back and clarify something. So I have magnetic field exerts force on a current, right? Notice I say current. I don't say on charges. I mentioned it could be moving charges, right? But that's the idea. It can't be charges at rest. And if you just have a wire, all the free electrons are just sitting there, all right? Because there's no battery here. There's just a meter. So that's the interesting idea, right? It's so hard not to make this. I don't mean to make a dumb joke here, but it really reminds me of Jurassic Park, right? Because current is like, the kids in Jurassic Park in the first movie, and the magnetic field is like the T-Rex. And if you don't move, the T-Rex doesn't notice you. If the charges don't move, the magnetic field doesn't notice them, right? It's only when the charges start to move that the magnetic field notices them and then starts pushing on them. Or in the case the T-Rex eats them, right? So that's the idea here. I think it helps kind of visualize it. But anyway, so we have all the pieces of the puzzle now. Faraday's law completes the relationship between electricity and magnetism, and a beautiful relationship it is. All right, so continue on. Electromagnetic induction. So induced voltages can be increased by, right? So if you're going to be changing a magnetic field, right, in order to induce a voltage and induce a current, how might you do that? Well, you can have more loops of a wire, all right? So that means that, you have a greater amount of what's called magnetic flux. So if you have more loops, then you're going to be able to get a bigger voltage, increasing the speed of the magnet entering and leaving the coil. So if I go, faster in and out, then I'm changing the rate of the flux. Thus, that's going to create a bigger current. Slow motion would produce very little current, but if you move it very fast, then you can get a lot of current and a lot of voltage. Okay. And again, the reason I keep lumping together voltage and current, if you don't recall, is because V equals IR. Right, and the resistance is the resistance of the wire itself, and so if you have current, you have voltage, and vice versa. Okay, that's Ohm's law. All right, so voltage is induced in the wire loop whether the magnetic field moves past the wire or the wire moves through the magnetic field. Right, so it doesn't matter what's moving relative to what, which makes sense because relative motion, it shouldn't matter, right? And so certainly we can have the wire moving or we can have the magnet moving, because the important thing is there's just a change in magnetic field strength by the wire. As long as the magnetic field strength is changing relative to the wire, then a voltage is induced. Okay? All right, so both of these are equivalent, moving the wire or moving the magnet. So when a magnet is plunged into a coil with twice as many loops as another, twice as much voltage is induced. If the magnet is plunged into a coil with 3 times as many loops, 3 times as much voltage is induced. So the number of loops is directly proportional to the strength of the voltage. Or the voltage, which is, I guess, the dependent, is directly proportional to the number of loops. So N loops. All right? Okay, good. So Faraday's law states that the induced voltage in a coil is proportional to the number of loops multiplied by the rate at which the magnetic field changes within those loops. Okay? The amount of current produced by electromagnetic induction is dependent on the resistance of the coil, the circuit that it connects to, and the induced voltage. All right? And that obviously ties in with Ohm's law. Okay, so it is more difficult to push the magnet into a coil with many loops because the magnetic field of each current loop resists the motion of the magnet. Okay, so that's because that's the strength that's being basically created by the coil. Okay, so the resistance when you feel when pushing a piece into a coil involves what? What's going on? Repulsion by the magnetic field you produce, energy transfer between the iron and the coil, right? Because that's the iron magnet. Newton's third law, because they're just pushing back on each other. Resistance to the main alignment in the iron. It's repulsion by the magnetic field you produce. Because what's happening is you're producing a magnetic field in that coil. Because of course we saw that, right? So once a voltage is induced in the coil due to the changing magnetic field, like plunging the magnet into the coil, well, now that coil produces its own magnetic field, right? And that new magnetic field opposes the magnetic field that created the current in the first place, okay? So the induced voltage and its associated magnetic field always opposes the original magnetic field. And that's such an important idea, but a little hard to wrap your head around at first, okay? So the voltage induced in a wire requires changing magnetic field in the loop by moving the loop near the magnet, moving a magnet near the loop, or changing the current in a nearby loop. All right, so those are the 3 ways we can create a changing magnetic field and thus induce a voltage. Okay, so application of Faraday's law, activation of traffic lights by a car moving over an underground coil. That's where you see where they cut out the road to add in those coils. Those are for automatic traffic lights. They work on induction. There's a lot of inductive chargers these days. A lot of phones are charged by inductive charging. You don't have to actually plug anything in. You just rest the device on top of a platform. So triggering security systems at the airport by altering magnetic fields in the coils as one walks through. That's a metal detector. Scanning magnetic strips on the back of credit cards, recording of sound on tape, and electronic devices and computer hardware, iPods, right? So many examples of magnetic induction. It's incredibly useful in all types of applications. Okay, so more about Faraday's law. More voltage is induced when a magnet is thrust into a coil. Okay, you know this if you've been paying attention, more quickly, right? The faster the change, the greater the voltage, okay? So not only is voltage induced when a magnet is thrust into a coil wire, but what else? Think Ohm's law here. Current, all right? All right? So it's definitely not energy or power because you can't create energy or power, right? There's a transfer of energy, but there's not a creation, all right? So one thing I want to point out a little bit is about the directionality of the current that's induced. So I'm going to go back real fast to the slide that kind of has the best opportunity to do that, which is this one here. So let's say we have a north end and a south end on the magnet. So that means that there's a magnetic field lines that point from north to south like this. Okay? Okay, so that's the direction of the field. And then what's going to happen is there's going to be an induced current. In what direction will the current be induced? Well, the current is going to be induced in order to create an opposing effective magnet. So what you want to do then is you want to make sure that the current is flowing in a way inside this coil, the induced current that is created by the changing magnetic field according to Faraday's law, that it's flowing in a way so that it will create a north end magnet upwards. All right, and we talked about how, if the current flows, then the magnetic field points in a certain direction. So you want to curl the fingers of your right hand so your thumb points up. Okay, so that would be in this direction like this. Okay, so this would be the direction of the induced current. And we know that because if I curl my fingers of my right hand in the direction that I drew on the slide, my thumb points up, which means now the effective magnet of the induced current has a north end. Right? Now this isn't a real magnet, right? This is just an imaginary magnet created by the magnetic field from the induced current. But notice that that north end points to the north end of the magnet, thus repelling the magnet. It's resisting the change, right? So the way to think about it is the direction of the induced current always resists the change of the magnetic field that created it, right? Okay, I know it's always like a big sentence. It's a clunky sentence, but the flow of the current resists the change. All right, and so here it has to create an opposing magnet, because then the north ends of the actual physical magnet and the effective magnet created by the induced current, those two north ends are going to repel each other. That's the idea that, when they say that you have to push hard, right? It's hard to push, difficult to push, because that magnet is opposing, the effective magnet is opposing the original magnet. All right, does that make sense? I hope it does. Okay, and that is called Lenz's law. Okay, the directionality and the fact that the directionality always creates an opposing magnet is Lenz's law. All right, so now we'll go back to where we were. Okay, so yes, conservation of energy. All right, now on to generators. Okay, so generators are absolutely an application of Faraday's law. How so? All right, well, they're the opposite of a motor, right? So a motor takes electrical energy and turns it into mechanical energy. A generator takes mechanical energy and turns it into electrical energy. Okay, converts mechanical into electrical via coil motion inside a magnet. It produces an alternating voltage and current. Okay, and the idea here is that we don't even need Faraday's law to understand a generator, but we will need Faraday's law to understand some details about the generator, including the idea of self-induction. But we know that there's, that here we're going to have charges like electrons. The charges are going to be moving in a certain direction. When the charges are moving perpendicular to the magnetic field, let's say that this is a north and this is a south, so the magnetic field line points this way. Well, when the charge is moving perpendicular to the direction of the magnetic field, then there's going to be a force on that electron. That force is going to be perpendicular to both the velocity of the electron, v, which is this arrow, which is the arrow right here, this arrow, and the direction of the magnetic field, which is this arrow. So that means that there is a force on the electron that points in this direction. That's the force. That force on the electron causes the electron to move, causes all the other free electrons in the metal to move, and that's your current. So the current is just the force acting on the charges because the charges aren't at rest, because they're spinning. They're spinning because of the mechanical input. That's a generator, okay? And the fact is that the direction of the force changes every half rotation, which is why it's alternating. And there's always a point where the velocity is going to be parallel, right? Think when this coil is oriented exactly horizontally, right? When the orientation would be like this, right? During that orientation inside the magnet, well, all the velocities would be parallel to the magnetic field or anti-parallel, which is just 180 degrees. And at either of those moments, there's no force at all. And so that's where the current zeroes out for a split second as the coil spins through that orientation. And then as it continues to turn, then the force builds up, thus the current builds up and the voltage builds up. Again, because the voltage just being, proportional to the current due to Ohm's law. Okay? All right, so that's the idea. That's why by the very nature of generators, they produce alternating current, right? That's fundamentally, it's the easiest type of current to create. All right, this is getting more into the idea, and we can see, right, that if we look at the voltage, we can see these parts where it zeroes out, all right? And it zeroes out every time the coil is in this orientation, because in this orientation, check out the velocities. the velocities of the free electrons are parallel to the green dotted line, which is the magnetic field. And whenever they're parallel, there is no force, thus no voltage. See, parallel again right here, parallel right here, right? Maximum voltage when the velocity is perpendicular. See? These are velocity vectors, right? And so that occurs with the maximum voltage, at least maximum in magnitude, even if it's negative, right? It's the magnitude that we care about, the distance from zero. Like a zero voltage means no current. Furthermore, you can think about what's going on with the actual free electrons on this section of our circular loop. Actually, nothing, right? Because their direction is never going. They're never going to experience a force that contributes to the current. So this section of wire, including this section here and here, don't actually contribute to the current in the case of a square loop. Obviously, it's more complicated if it's a circular loop, but in a square loop, we can actually just write off these two sections of the wire, and the only ones we care about are this section and this section. Okay? All right, so using Faraday's law and Henry's discovery of electromagnetic induction, Nikola Tesla and George Westinghouse showed that electricity could be generated in sufficient quantities to light cities. Pretty amazing, right? So it's the idea of creating an AC current. All right, furthermore, you can have a particular type of current generation, MHD, magnetohydrodynamic generators. This is just kind of a more modern application. It eliminates the turbine and spinning armature altogether. A plasma of electrons and positive ions expands through a nozzle and moves at supersonic speed through a magnetic field. The motion of the charges through the magnetic field gives rise to a voltage and flow of current as per Faraday's law. Pretty remarkable. All right, and so essentially you just have to have conducting plates, and then the current builds up on those plates. So you don't have to have anything turning. You just shoot plasma through a narrow nozzle, and there you go, right? So you can eliminate a whole source of inefficiency, which is, the friction on the actual pivot point, right, on the axle. Okay? So another amazing application of Faraday's law is the idea of transformers. And this is so crucial because this means that we can generate power at a certain voltage, but then have a different voltage in our homes. Okay? So let's talk about it. So what is a transformer? Well, it has an input coil and an output coil. So the input coil of wire, the primary powered, which is the primary powered by AC voltage source, and the output coil, also known as the secondary coil, is the secondary connected to an external circuit. All right. So we have the power come into the primary, and then we have the secondary come out and then get used for something like powering light bulbs in our home. Okay. So what's going on with that? Well, the idea of the transformer is the voltage won't be the same if the number of loops differ. So here we have 1, 2, 3, 4, 5 loops on the primary, but only 4 loops on the secondary. And that means that there will be a voltage change due to the relative number of loops on those two coils, okay? And notice they're not touching each other, but what's happening is the current in the primary is creating a magnetic field. That magnetic field is not a steady magnetic field because this is an alternating current. And that's so important. This would not work with a DC current. Transformers do not work with DC current. Because if it's DC, then it's just a steady magnetic field, and that steady magnetic field cannot induce another current, okay? Never works with DC. But if there's alternating current, then the direction is going back and forth. Thus, the magnetic field that's being created by the primary coil, and this is just an iron core here, right, just to increase the strength of the magnetic field. But the magnetic field that's created by the primary is varying. That varying magnetic field thus is capable, according to Faraday's law, to create a second current in the secondary, right? So it induces a current in the secondary coil. And then that secondary coil will have a different voltage because it has a different number of loops, all right? Okay, so transformers, more about them. All right, so both wound on a common iron core, so the magnetic field of the primary passes through the secondary, right? That's kind of the setup. It uses an alternating current, remember it only works with alternating current, and voltage in one coil to induce an alternating current and voltage in the secondary coil. Because obviously it can't create a steady current because the magnetic field is varying, and and every so often the magnetic field is zeroing out, so thus the output of the secondary is also going to be AC, right? So everything about it is alternating. All right, so transformers can be step up or step down. All right, so a step up transformer produces a greater voltage in the secondary coil. All right, and so in that case, the secondary has more turns in the coil than the primary. All right, so a step up transformer steps up voltage, but it steps up voltage at the cost of current. So if voltage goes up, current must go down. And we know that current must go down because power is VI. and the power can't change, right? There can be a loss of power, due to inefficiencies in the system, but you can't just have energy created from nowhere, which means if you increase something, you have to give something up. So if the voltage goes up, which is what the step up refers to, an increase in voltage, then current must go down. In a step-down transformer, you're decreasing voltage, so maybe from a high voltage that was used to transport electricity over long distances, and you step it down to be used in commercial or residential homes. In that case, the current goes up, right? Which is fine. It's kind of an undesirable side effect because it means that we have a ton of current, which means you can get easily electrocuted. But it is, but you definitely don't want to have high voltage either. But it does mean that you step up current when you step down voltage, right? So step-down transformers produce a small voltage in the secondary, and supplied by the primary, and the secondary in that case has less turns, right? So if you want to step down, you go from many turns to fewer turns. Okay? All right. So here's the formula, really the only formula from the chapter, which is you can think of it as a transformer relationship or the transformer formula, and it's primary voltage over number of primary turns equals secondary voltage over number of secondary current turns. Okay? So that allows you to solve for the change in voltage if you're given the number of turns. Or you can solve the number of turns if you have a desired change in voltage that you're asked to find. The transformer transfers energy from one coil to another. The rate of energy transfer is power. So the power into the primary equals the power into the secondary, all right? So voltage times current equals voltage times current. I was talking about this, right? Because I wanted to make upfront about it that that energy is conserved here. It better be, right? All right. So transformer transfers energy from one coil to another. So voltage stepped up before leaving power station. The voltage is stepped down for distribution near cities by cables that feed power to the grid. And the voltage stepped down again before being supplied to businesses and consumers. All right, so a step-up transformer in an electrical circuit can step up what? All right, but it's definitely voltage. Definitely not. It's not energy because we conserve energy. Okay, an efficient transformer is in an AC electrical circuit can change, what is it? Well, current. Can't change power or energy, right? So current carrying loops in a coil interact not only with the loops of other coils, but also with the loops of the same coil, okay? So think about that. So anytime that you create that magnetic field, think about the example I talked about, Lenz's law, where there's that induced current flows in a certain direction to create a magnetic field. Well, here's the thing. Now that magnetic field that's created, it's going to affect the charge that's actually flowing in that coil. So that's the idea, is that every time you have a changing current creating a magnetic field, well, even a steady current creates a magnetic field. That magnetic field then acts on the current that created it. That is self-induction, all right? So each loop in a coil interacts with the magnetic field around the current in the other loops of the same coil. This is self-induction. When the switch is open, the magnetic field of the coil collapses. The sudden change in the field can induce a huge voltage. All right, so you can have these big voltage spikes when there's a sudden change. Okay, and a big consequence of self-induction is, as I said in the introduction, is this idea of back EMF. Because anytime you have a motor, that motor then is you're basically putting a AC current into the motor, right? You can also have like a DC motor if there's a gap, there's a point where just the direction of the current changes, right? You can make a DC that acts like an AC, but just having a switch that opens and closes in an alternating way. But the point is that when that's happening, when you're running that motor, and then that motor then is turning, it's then creating a changing magnetic field that is inducing a current. That current actually opposes the current that turned the motor in the first place. So the very act of the motor running creates an induced current that runs backwards from the current that ran the motor. Because remember, the only reason the motor is running in the first place is because of the force acting on the charges, right? And the reason there's a force acting on the charges is because you're moving the charges by pushing them with a battery or pushing them with some other power source. But the point being is then that opposing current is the back EMF, and motors are designed to always have an opposing current. They're not made to run with just the forward current. That's why motors will overheat if they stop moving, because now there's too much current flowing through the system based on its specifications, and it can't handle the actual output of energy due to that much higher current, because now the back current isn't there anymore, and so you've got like a big number without the subtraction, okay? So a little bit about power transmission. Almost all electrical energy sold today is in the form of AC because of the ease for which it can be transformed. Remember, because transformers work with AC, they don't work with DC. All right, large current in wires produces heat and energy losses, so the power is transmitted great distances at high voltages and low currents. So yeah, that's one of the great advantages of step up. You can step up that voltage and really lower the current. Okay, so power is generated at 25,000 volts or less, and it's stepped up near the power stations to as high as 750,000 volts. So it's actually stepped way up higher than the power plant that actually produced it. That way it can be transmitted over long distances at relatively low power loss. It is then stepped down in stages at substations and distribution points. Because that's really high voltage. We have to obviously step it down, and you don't want to step it all down at once because there'd be a lot of inefficiency that way. There still are inefficiencies. All right, so last idea here, field induction. Okay, so electromagnetic induction is a two-way street. It's a great way to think about it, okay? So Faraday's law states that an electrical field is induced in any region of space in which a magnetic field is changing with time. Well, Maxwell took that idea and said, okay, there's obviously a lot of symmetry and connection here. So what he said is, okay, well, if a magnetic field is induced in any region of space in which an electric field is changing with time. Oh, okay. So that means that sure, you can create a electrical field by having a changing magnetic field, but you can also create a magnetic field whenever there is an electric field that's changing. Now we know you can actually create a magnetic field with a steady current. All right. Well, what is a steady current? A steady current is actually a change in an electric field. All right. So this is the complete idea. The idea that a changing magnetic field creates a changing electric field. A changing electric field creates a changing magnetic field. Okay? So one causes the other, and so on. You can have a chain reaction. All right? So the mutual induction of electric and magnetic fields can produce light. All right? And that's going to be a topic that we're going to be running with now for many chapters. So light is produced by the mutual induction of electric and magnetic fields. That is really what light is. Light is an EM field, electromagnetic field. Okay? Speed of light is the speed of the emanation of these fields. All right? So these fields are based on two constants called the permittivity and the permeability constant. The speed of light is actually derived from those two constants, those two empirical constants that we find by measuring the effects of fields. That's where the speed of light comes from, and then it's confirmed through other experiments. So we can really see that not only theoretically is light created by a changing magnetic field and a changing electric field, and them changing each other, light is also matches up with the numbers and the values that we have that we can actually experimentally measure. Okay? So too slow, the regeneration field dies out. Too fast, the field builds up in a crescendo of ever-increasing energy. At the speed of light, c, which is just equal to 3 times 10 to the 8 meters per second, you have perfect balance and you have light. Okay? All right, well that wraps up our introduction to electricity and magnetism. I hope it has been interesting and informative. Thank you for watching.